And that's actually it for the changes before we can dive into the depths of the actual sound playing. So play sound name just looks up the name and effect buffers, plays buffer. Play buffer creates an audio buffer source, connects it to that wave shaper node to do the clipping, and assigns the buffer and starts it. So those are all things I showed last time. Now, I have this constant for the audio rate. I'm doing 48,000 samples a second. CDs are 44,100. The maximum you can usually rely on a browser giving you, in theory, is 96,000. But even then, it might downsample in the actual playing. 48,000 or 44,100 are kind of the normal default values you would use, unless you have some specific requirement otherwise. Song notes. This is an array. It's some numbers and some nulls. Those numbers are actually relative pitches I just worked out in LMMS. And I transcribed those numbers in nulls for where there isn't a note because the note's being held. And that's the song in terms of just relative abstract pitch values rather than actual notes. I use that to generate song buffers. So, for each of those sound names I'm using, I'm calling my make effect function with different parameters. And for the song buffers, for each song note that's not null, I'm making a note. And I make sure the song buffers array is the same length as the song notes array. This code here won't populate the trailing elements because the song notes are null, but I still need to have the song buffer length correct so that that modulus loop at the end of it works correctly. So I'm using the array constructor instead of making an empty array. So I'm using make effect and make song notes to make little bits of sound. Let's look at make effect. Taking a bunch of parameters, length in seconds, frequency 1 in hertz, frequency 2 in hertz, volume 1, volume 2, and style, which is going to be either honk or noise. I'm making a buffer. The length of the buffer is this length in seconds converted to audio samples at the 48,000 samples per second rate. I'm getting the data from that so I can write into it. And I'm using two numbers here. Phase is tracking where I am in my waveform. As my frequency changes, I don't want my waveform to abruptly replace itself with another waveform of a different frequency. I want to keep the wave where it is and change the frequency going forward. So the phase is all I need to track that. Phase is basically if I'm like moving around in a circle, the phase is like the angle on that circle that I'm at. And if I'm higher frequency, I'm moving faster around the circle. Lower frequency, I'm moving slower around the circle. Noise is a variable that I'm only using when style equals noise, but it just didn't happen to have an if statement there. It could have only initialized when style equals noise, but one called a randomizer, whatever. Noise is a random number from -1 to 1. Now, I iterate over this channel data, the number of samples in my sound. I have this vol variable I need to take care of. So, first of all, I'm going to set the volume to a different value depending on whether I'm halfway into the sound or not. Less than halfway in, I'm ramping up. More than halfway in, I'm ramping down. And I chose these parameters so that ramp up and ramp down meet each other at the same point. So there's not a discontinuity at the middle. If I just divide by 4 just to scale it down arbitrarily, I could have just passed in smaller numbers to begin with. Now the frequency, I am sliding smoothly between freak 1 and freak 2, and this is so that linearly interpolates. At freak 1, this comes out to, no, at 0, this comes out to freak 1. At I equals sound.length, this comes out to freak 2. This is a staple piece of thing that one does a lot when linearly interpolating. It's just kind of a canned thing to remember. Just the current thing over the number of things I have times the difference between the endpoints plus the initial endpoint. And likewise, I'm multiplying volume by that same construction over the volumes. So my frequency is going to be a linear slope from freq 1 to freq 2. My volume is going to be a linear slope from volume 1 to volume 2 times this other stuff, so that my volume is actually going to be a ramp up, ramp down in addition to the volume slide. Then, depending on my style, the actual value I put in the sound array differs. If my style is a honk, then I'm doing the same thing I did last time with the phases. I'm incrementing my phase by frequency over audio rate, taking the modulus 1, and then if that's less than an eighth, I'm at low volume, otherwise I'm at high volume. In this case, I had a constant instead of a vol. Now I have the vol value, so the volume's ramping over the course of it, but it's the same wave shape in general as last time. If my style is noise, then I'm checking whether my phase has looped. If my phase has looped, then I reset my noise value. Otherwise, I keep the same noise value as before. And then I set my sound to that noise value times vol. It occurs to me this could be easiest to demonstrate using Audacity. I am setting Audacity up to record out of my own speakers. This is JavaScript. I can't just go right in here and call a function. Play sound kit. Yeah. You see, this is a very, very random looking wave, but if you zoom in, it's only re-rolling the randomness every so often. That's producing a sound which, instead of being a pure white noise, is a kind of tuned sort of white noise. It's how a lot of chiptune noises work, including the NES, the C64, the Game Boy. Most of your 8-bit noises were like this. You could set the frequency to change how often it re-rolled the randomness. And once we have this values populated, then we return the buffer. So we've made the buffer the appropriate length. We've gone through and made a waveform, tracing out a curve with a volume ramp up, volume ramp down, sliding volume scale, sliding frequency scale, and the wave itself being either an 8th phase pulse wave or noise that gets re-rolled at the frequency. And we return that buffer. That gives us our effects. Now, make song note does a sine wave. It is doing a little bit of attack and decay. Let me go from the start. First, we need to figure out how long our note is. So there's at least one thing long. Let me find the thing. So critically, the var I in song notes is the index into this array. So when I call this, I'm getting an index. So if I call this with 1, then I'm seeing this element, but I'm getting the number 1 to start with, not the 5. And I'm asking myself, how long is this note? So I'm going from the next element forward. If it's null, add to the length, otherwise I'll break out of this loop. So I see how many nulls follow it. This plus n happens for an interesting reason. Annoying reason. Interesting reason. When I do var I in something, I is always a string, and if I need to use it as a number, I have to explicitly cast it to a number, which in JavaScript, one way to do that is plus on it. So that's why that weird plus is there. When I add it as n plus 1 without that extra thing, then it was turning the 1 into an 11, and it was just weird. Anyway, I have my note length. Now I make the buffer for that length. So audio rate over 3, a third of a second, times the length. But I want a little gap between notes, so I'm subtracting a quarter of that from the length. So it's subtracting a 1/12 of a second. So now I have my buffer. Now I need my frequency. And a semitone differs from another semitone by a 1/12 of an octave, and this is a logarithmic scale. What that means is the frequency here is twice the frequency here. And it turns out, mathematically, what you do is take your semitone, divide by 12, and raise 2 to that power. That gives you the curve. Then you multiply that by whatever note 0 happens to be, which I arbitrarily picked at 180 after just listening to different numbers. So that gives us from that integer a frequency representing the actual hertz value of a note. And now, in this array, I have a volume setting, which is normally a half, but if I'm very close to the beginning of the note, or very close to the end of the note, then I have a little ramp attached to it. So it's an attack and decay, or attack and release, depending on how you want to look at it. Basically the same as how LMS does it in some sense. It's a linear ramp up, a held volume, a linear ramp down. And then I make my sound. So like I explained last time, you scale by 2 pi times frequency over audio rate, and that gives me my sine wave for the note at that frequency. Multiply that by the volume to get my attack and decay, and return that buffer that I just populated. So that makes the song notes, that makes the effects. This init audio buffer is happening on load, so before anything else happens, I have my effect buffers and song buffers. And then game events called play sound to trigger these. And the things that need the song go through song buffers, one element every third of a second, and play the elements there. And that's how I added sound effects to this game. It's not like I couldn't make more complex sound effects, but I feel that for the level I'm going to put into the graphics, these are going to be good enough sounds. I'm not going to make the graphics high-tech at all. And high-tech sounds with low-tech graphics, there's games that done that well, but I prefer that they kind of similarly lo-fi. So that's it for audio, and I will see you later with the next one. Bye.